short presentation, a set of short presentations, and let me just bring the slides. Just 1 minute. So we have a set of presentations there. I'll try to introduce the speakers in 2 batches. Arpan presented it yesterday, one of the short presentations. So today he will be focusing a little bit more. I gave this example of the large pathology example, so he will go into more details. So he's a 3rd-year PhD student at the Ohio State University, and he's focusing on HPC libraries and deep learning. So he will present on training of very large-scale pathology images using MAPS to GDR. Then it will be followed by Dr. Aamir Shafi. He's a research scientist at OSU, where he's currently involved in the high-performance big data project. He was a Fulbright visiting scholar at MIT, where he worked on the multi-core Silk technology. He was also the main architect of a Java-based MPI library called MPJ Express. Aamir has a PhD from the University of Portsmouth, UK, and a BE software engineering degree from University Pakistan. So he will be focusing more on the efficient communication support for Dask using MAPS to GDR. He will also be giving another talk, that is the second talk, which is the Parallelizing GPU accelerated machine learning applications, also using MAPS to GDR. So then we have the 3rd presentation will be by Qinghua Zhou. He is a PhD student in the OSU network-based computing lab. He's also working on the MAPS to GDR, so he will be talking about the benefits of GPU-assisted on-the-fly message compression. I indicated some results yesterday in my talk, but here in this talk, we'll go down into more detail. So let's go over the first 3 talks, and then I'll try to introduce the others. So might be Arpan. You
Dr. Panda, you are ahead of the schedule. Like if you go to the previous one, that is before this.
Oh, sorry. I put okay. So then let me introduce both. My mistake. I think it was in that page. So we'll go in this order. So it will be presented. The first talk is by Jahanzeb Hashmi. So Dr. Hashmi is a senior research associate in the network-based computing lab. He graduated recently from the group. So he has been working like whatever the earlier in my talk I presented about XP MEM and all. So those are his work in the MAPS to X. And his research interests include performance engineering, architecture-aware communication algorithms, parallel programming models and runtime systems, and distributed deep learning. So he's currently working on the MAPS to project where he focuses on architecture-aware hierarchical algorithms, communication optimizations for highly parallel CPU and GPU architectures, and scalable deep learning. So today he will go into more details on the exploiting AMD GPUs with MAPS to GDR. If you remember yesterday, I indicated we have just started working on the AMD GPUs. I showed some preliminary numbers yesterday. Within the last 24 hours, we have much more numbers. He will try to share those. And then the next presentation will be by Kawthar, Shafi Khorassani. She is a 3rd-year PhD student working again on the MAPS to GDR project. Her research interest lies in the HPC and GPU. So she will go into more details on the Alltoall and Allgather support. Again, I showed some initial number yesterday in my talk, but she will go into much more details on that. And the 3rd talk will be by Quentin Anthony. He's a PhD student, also in the MAPS project. He's working on both on the MAPS side, MAPS to GDR, and also the high DL. And I showed some numbers again yesterday with PyTorch and Deepspeed with MAPS to GDR. He will go into much more details on how do we scale this on very large scale system and the optimizations we have done and how does it compare to other libraries like Nickel and all. So I think I introduced them in the reverse order, but sorry for the problem. I think we can then just go through the talk one after another. So maybe we'll start with Jahanzeb. I think we'll go strictly in the order printed in the program. Yeah.
Hi.
Please.
Can you see my screen?
Yes. Please go ahead.
Okay. Hi, everyone. And Thank you, Dr. Panda, for the introduction. And so this is a short talk regarding our initial work that we are doing in collaboration with the AMD folks. And so the talk is regarding exploiting AMD GPUs with MAPs to GDR. As we all know that my slides are not. Yeah. Okay. So as we all know that the future exascale system is going to be AMD hardware based. So the two of them, El Capitan at Lawrence Livermore and Frontier at Oak Ridge National Lab, is going to be the potential next exascale system. But even before going to the exascale era, that the current and upcoming systems, as we have seen in the earlier talks, that they are trying to employ AMD-based hardware, both in the CPU as well as GPU side. And I'm not going to talk much about the CPU side, but more focus on the GPU side. And AMD's Radeon Open Compute, like also called ROCm, is basically a software ecosystem which provides a set of high-performance APIs for the high-performance computation and communication. And on the other hand, MAPs to GDR is a widely used MPI library for GPU-based device-to-device and host-to-device-based communications, which employs several data movement optimizations and several other optimizations regarding the MPI's implementation onto GPUs. It started off in early 2014 with the NVIDIA's CUDA APIs, and then now we are at the point where we are trying to incorporate the support for AMD's ROCm ecosystem as well. So in this work, which we have just carried out as an initial version, we're trying to extend MAPs to GDR and have an initial support for AMD GPUs, and we have done some basic point-to-point and collective communication implementation. We are exploiting the peer direct, which is similar to the GPU direct RDMA features of NVIDIA, and AMD also provides a large bar feature, which is an alternative to NVIDIA's GDR copy feature, and similar to NVIDIA's peer-to-peer IPC. ROCm also has a peer-to-peer based communication. So all these are exploited in the MAPs to GDR ROCm support. And we have some optimized staging-based pipeline design for the larger messages, as we'll be seeing some numbers. But keep in mind, this is the initial work, and we still have a long way to go. We still have to do a lot of tuning and a lot of optimized support still needs to be done. And this is just a sneak peek of what to expect in the coming releases. So we use before I continue, I would like to thank a lot the AMD folks, especially Park Louis from AMD and Saurabh Chakraborty from AMD, who have been working very collaboratively with them, and they have been very responsive. And whatever the issues we have encountered regarding the system-wide and the software installation and everything, they were very quick to respond to that. So they were generous enough to give us the access to their system, which is state-of-the-art system. So here's the configuration that we used. So the CPU is an AMD ROM 7742, which has dual socket, and each socket has 64 cores. And GPU is a Radeon Instinct MI50, which is state-of-the-art AMD GPU. And there are 8 GPUs on each ROM node, and there are four GPUs connected via HDMI within a socket and via PCIe over across the socket. And the network is a Mellanox STR 200 Gbps adapter. And ROCm version, we use 3.7, and MOFET is 5.0, and the stock compiler from Ubuntu. So just the basic numbers. So this is an internode latency from device to device. So the sender's buffer is on one device, and the receiver's buffer is on a remote node device. As you can see that we have and we have compared the performance with the OpenMPI's UCX implementation of ROCm using based on OpenMPI. And so we see this 2.94 microsecond latency for 1 byte message, and this is close to OpenMPI plus UCX as well. And as we are increasing the message size for the medium message, we have to still do some tweaks and some tuning. So that is in our roadmap. But for larger messages, it's a similar performance that we're getting from as compared to the UCX. So this is internode bandwidth, device to device. Still the same story for the small messages. We are more or less similar. And in the medium message range, we have some room to improve, which we're working on. And for the larger messages, we get a good benefit as compared to OpenMPI plus UCX. So this is really work in progress. And we have by bandwidth result here where we are getting up to 18.2 gigabyte per second, which is still not the peak HDR bandwidth, but there is still some room to improve. But I think the same issue is happening on the UCX side as well, and they are also trying to work on the large message bandwidth and by bandwidth as well. And so intranode, we had encountered some system instability and some numbers which we were not able to make sense of. So we are still trying to investigate. So those are omitted for now. But here I'm just trying to show an Allreduce performance and in terms of scalability for 3 different message ranges, as you can see. This is not optimized. This is not tuned. We just ran vanilla MFH to GDR with ROCm support, which will be using the point-to-point based operations to orchestrate the collective. And same thing is for OpenMPI as well. So please note, this is without any tuning. We just wanted to see whether things are working at scale out of the box. As we are seeing, MFH is working for all the message ranges. So this is on 128 GPU result for 4 byte small message range. So from 4 byte to 1K small message range, 2K to 512K medium message range, and from 1 megabyte to 256 megabyte, which is very large message range, typically used by the deep learning workloads. And we are seeing that MFH is working just out of the box. The absolute numbers may look quite high, but that is expected because there is no tuning and optimization done yet. But things are working out of the box. Same goes for OpenMPI as well, but so the things are working, but they are slow, and that I attribute to probably the algorithm selection for the device-to-device collective operations. So I hope that will improve as well as we move forward. And so this is another a different kind of result which shows the scalability. So for example, we fix the message size to 4 bytes and scale the number of GPUs. So 2, 4, 8 to up until 128 GPUs, and we see a very linear trend with the short message Allreduce. Like for example, we can get a 128 GPU 4 byte Allreduce takes about 11 or 12 microseconds. And same trend is for the medium and large messages as well. UCX was very slow for the very large messages, and that it did not run to completion, but I believe that will improve in the future. So yeah, so with this, I would like to conclude. So we have seen that upcoming large-scale systems are going to heavily use AMD's hardware, and we are trying to get our software ecosystem getting ready for that. And MFH2 is the widely used library for GPU communication, and we just added initial support for AMD GPUs for point-to-point and basic collective operations. But there is a long way to go that we have to do lot of optimizations and tuning for that. And as a set of next steps that we'll be focusing on running the deep learning workloads on via Horoward onto the AMD hardware. This is still work in progress. You will see some numbers in future. And the other thing is that, as you may have noticed, that the collective comparison is done within MPI. We have not compared against RICL because that uses the kernel-based reductions and collectives, which MFH ROCm port has still not enabled yet. So that is still work in progress, and in future we'll be seeing that. So with that, I would like to conclude. And if you have any questions, please feel free to ask. Thank you.
Any questions from the audience? Okay, since we have we're running a little bit late, let me start moving. So if you people have any questions, please feel free to ask on the chat or on the QA box or on the Slack channel, and might be the next one. Kawthar, can you please proceed? Yeah, the slides are there. Yeah.
All right. Okay. So hi, everyone. As mentioned earlier, I'll be going over high-performance Alltoall and Allgather support for dense GPU systems within MFH2 GDR within the next release. So this will be a very brief presentation highlighting some performance enhancements within the MFH2 GDR library. And the motivation for this is that with GPU-based collectives, we typically hear about Allreduce due to its current relevance. But now these kinds of enhancements in GPU-based Alltoall and Allgather are more relevant as we see MPI Alltoall being used for matrix transpose or fast Fourier transforms. And we also see more Alltoall and Allgather being used for model parallelism for DNN training on GPU clusters. And on this note, we see an interest in evaluating and enhancing the performance of these GPU-based collectives for different platforms. So throughout the presentation, I'll include some other CUDA-aware MPI libraries. So I'll evaluate MVAP-2 GDR default version 2.3.4, and then also compare that to the optimizations and tunings that we have in MVAP-2 GDR 2.3.5, the pre-release version. I use Spectrum MPI 10.3, which is available on systems like Lassen and Summit, and then OpenMPI 4.0.4 plus UCX. And then I'm doing a benchmark level evaluation using OSU Allgather and OSU Alltoall in the OSU micro benchmarks. So first evaluation is on Summit, which many of you may know is the #2 system. It's an open power, has open power nodes equipped with dual socket CPU and 6 volt to GPUs, 3 GPUs per socket. So this is the performance on 32 GPUs for Alltoall, comparing MVAP-2 GDR 2.3.4 and then the pre-release version. We see significant performance enhancement due to our tuning and optimizations for small message ranges, and then also in the large message range beyond like 1 megabyte, we see approximately 20% improvement throughout. That's also for 64 GPUs, we see similar trends as well. And then when we scale towards 128 GPUs and 256 GPUs, again, we see a lot of enhancements in the small message range from MVAP-2 GDR 2.3.4 to the pre-release version, and as well beyond 1 megabyte, we see approximately 2x improvement. Now for the Lassen system, on Lassen system, very similar to Summit system, with 4 GPUs per node, 2 GPUs per socket. On the system, we evaluate Allgather and Alltoall with the other CUDA-aware MPI libraries as well. So for 16 nodes, 64 GPUs, we see comparing MVAP-2 GDR 2.3.4 and the pre-release version, we see a lot of enhancements in the larger message range. So about 1.5x on both 64 GPUs and 128 GPUs. And then also for Alltoall, we see enhancements. It's less visible over here, but we also see some similar trends with Alltoall compared to what we saw in Summit due to some limitations. It's not showing numbers beyond 1 megabyte, but you would also see the similar trends beyond 1 megabyte that we were seeing. And to conclude this talk, optimizing the performance of GPU-based collective communication is becoming more relevant across different collectives and for different platforms, especially as we see Alltoall and Allgather used more frequently in scientific applications. With our next release of MVAP-2 GDR, you'll see improved small message Allgather and Alltoall, and significant improvements there, and then also enhanced improvements in the larger message range we saw to 1.5 to 2x improvement, and these will all be available in MVAP-2 GDR 2.3.5. All right, any questions?
Yeah, any questions for Kawthar? Okay, so if not, again, please feel free to post your questions into the QA box. Let's move to the next one. I think the next one is Quentin, Anthony. So please proceed.
Hello, can you hear me?
Yeah.
Okay, hello, I'm Quentin Anthony. Today, as previously mentioned, I'm going to be talking about scaling distributed PyTorch and Deepspeed with MVAP-2 GDR. So first, let me briefly introduce deep learning. Deep learning is a subset of classical machine learning where the training features are automatically extracted from the training data by the model, as opposed to the handcrafted features of machine learning. So the reason deep learning is so popular now, given that a lot of the theory was completed back in the 80s, is that computing power has finally caught up. So we're able now to train practical deep learning models in a reasonable time frame. So distributed DNN training consists of two phases, forward pass and the backward pass. And given these, HPC systems have become increasingly popular for emerging deep learning workloads. And to meet this need for deep neural network parallelism, 3 strategies have emerged. One being data parallelism, where you fully clone the DNN across worker nodes and then update each local model at each global training step with an Allreduce operation. Model parallelism, where you split the model itself across compute nodes. And hybrid parallelism, where you split the model across a set of nodes, then perform data parallelism across each set of nodes. So the most widely adopted scheme currently is data parallelism, and this is due to its simplicity and the fact that most models fit inside GPU memory. Data parallelism will be the focus of this presentation. So PyTorch is an open source deep learning framework backed by Facebook's AI Research Lab, or FAIR. PyTorch has recently expanded in popularity due to a few key features. One being a simple Python interface. They also provide support for C++, but Python is their main language. They have extensive optimization for GPUs and a distributed model for data parallel training that provides support for both Nickel and MPI. They have a few key differences from TensorFlow that have caused them to become so popular. One being PyTorch's API is much simpler and allows for faster prototyping than TensorFlow's. Another being TensorFlow's data parallel support is much more complicated to run with and requires more prior system knowledge. So as a consequence, PyTorch has been widely adopted by the research community in particular. And as you can see in the figure here, PyTorch is now used in the majority of papers for most DL and ML conferences. So given this recent dominance of PyTorch in the research field, and its ease of use for distributed training, as well as the growing need for distributed training on emerging DL workloads, there's an increasing focus on distributed PyTorch. While classic distributed DL training with Horovod can be performed with any of the major DL frameworks, being TensorFlow, PyTorch, and MXNet, an emerging distributed DL framework called Deepspeed only supports PyTorch. So we'll examine these 3 distributed DL frameworks, Horovod, Torch.distributed, and Deepspeed, on HPC systems and on MVAPIS2 GDR for GPU training. So before comparing performance across these frameworks, we'll first compare across HPC systems. So Summit is the #2 supercomputer with 6 Volta GPUs we saw in Kawthar's presentation before. And each GPU is connected via NVIDIA NVLink. So Summit is hosted at Oak Ridge National Lab, but we train the ResNet 50 DNN on synthetic data, which is just random numbers, in the format of ImageNet to measure throughput performance. And we use ResNet 50 due to its popularity in the deep learning community. So we scale training on this data set to 256 Summit nodes, which translates to 1,536 V100 GPUs. We're able to beat the throughput of NVIDIA's collective communication library, or Nickel, by up to about 30%. Then we would go to a different system, the Lassen supercomputer, which is number 14 on top 500. It's also via NVLink, but 4 Volta GPUs per node. While we didn't go to as large of a scale on the system, 256 GPUs instead of 1,536, we still observed about a 50% improvement in training over Nickel. We use the same scale to compare each of the 3 distributed DL frameworks with PyTorch support, being Horovod, Deepspeed, and PyTorch's native Torch.distributed. So these are the numbers with Deepspeed. We still beat Nickel for Deepspeed, but we're also able to achieve more throughput than Horovod by about 10,000 images per second at 256 GPUs. This is because Deepspeed has more effective optimizations for data parallelism than Horovod, but we're still exploring where precisely this is the case and by how much, and which optimizations are causing the most increase in throughput. While the improvement over Nickel still stands for PyTorch's native Torch.distributed module, we found the lowest overall training throughput with this framework. This is because they have the least support for data parallel optimizations, and I'll explain that more in a later slide. So here I compare all 3 frameworks at 256 GPUs on Lassen. The throughput performance of Nickel and MVAPIS2 GDR is compared, and as we can see, MVAPIS2 GDR performs better than Nickel for all 3 frameworks by about 10,000 images per second. So since the same benchmark, the Resonant 50 on synthetic data, was used for all three frameworks, we can also compare the performance across these frameworks. So we can see that Horovod performs significantly better than Torch.distributed, and Deepspeed performs slightly better than Horovod. So we'll understand a little bit more why in the next slide here. So while we need further profiling information to determine which framework optimizations contribute the most, as I said before on a previous slide, there are several optimization options that contribute to the performance difference. So many of the optimizers there provide different benefits for different GPU and interconnect combinations. So we expect the performance differences across frameworks to change depending on the system. Horovod provides support for tensor fusion, which batches small update tensors to a single Allreduce call at each training step. And then larger messages provide better throughput. They also support hierarchical Allreduce algorithms, as well as floating point 16 gradient compression. Deepspeed, on the other hand, implements the 0-2 parallelized optimizer, which partitions the model state across workers. So this is what we're still exploring and why this provides such a benefit. Torch.distributed provides a much more basic version of Horovod's tensor fusion, which they call bucketing, which again is just batching the update tensors at each training step. In conclusion, we've performed an in-depth performance characterization of data parallelism with PyTorch. The main insights we can gain from the study is a dominance of specialized distributed DL frameworks, namely Deepspeed and Horovod, over the basic distributed support such as Torch.distributed. So these specialized frameworks are designed to perform better on HPC systems with high-speed NVLink or InfiniBand interconnects. Part of the key insight we want people to gain, including us from this study, is that you use Torch.distributed for more specific workloads like model parallelism or edge cases, but for something as bread and butter as data parallel distributed training, you should use a specialized framework. Finally, MVAP2 GDR performs much better than Nickel for PyTorch workloads, which is justified by the prior performance evaluation on large systems. So thanks, that's all I have today. If you have any questions, feel free to ask.
Okay, I don't see any questions in the QA box. We can start moving to the next one. It will be Arpan.
Hello.
Yeah, your slides are there. Yeah.
Okay. So, hello everyone. I'm Arpan Jain. Thank you, Dr. Panda, for the kind introduction. So today I'm going to talk about the training of out-of-code deep neural networks on high-resolution images like we have in the pathology using the MUG'20 GDR. Oh, 1 second. Yeah. So thank you, Quentin, for covering the deep learning basics. So now I can move to the more advanced step directly. So we have parallelization strategies, and normally we can divide it into 3 types: data parallelism, model parallelism, and X parallelism, be it spatial or channel parallelism. So we already know about the data parallelism. 1 second. Yeah, we already know about the data parallelism. So in the model parallelism, we are distributing the model across the multiple nodes. And in case of spatial or channel parallelism, we are distributing the layer itself. So when we are talking about the distributed deep neural training, 90% of the time, researchers are talking about the data parallelism. It is fair, it is very easy to use, and you can use it on most of the models. However, there is an inherent problem with the data parallelism. So if your model cannot fit inside the memory of your machine or your GPU, then you cannot use that. You cannot use the data parallelism to train your model. So let me show you a result. So in this case, so I'm showing that on the x-axis we have the image size, and on the y-axis we have the memory consumption. So as you can see that on the ImageNet data set, you can train your model using the data parallelism. But as you increase the image resolution or image size to 1K into 1K or 2K into 2K, you cannot use the data parallelism. And the problem is that the model is very, very big and it is consuming so much memory that you cannot fit that model into single GPU, even with the batch size 1. So that's why we need model parallelism for such kind of models. And when we are talking about the pathology, we are in a whole different area. So it is good, we can train the model with the model parallelism, but model parallelism is not very efficient. It does not give you the very good performance. So let me show you a result first. So basically, suppose that you have a model that can only be trained on 4 GPUs. So if you are training it on the very large images, then it is possible, in most of the cases, it is like only the maximum batch size you can train it with is 1. So this is how it will behave. So this is how the memory utilization will be for the forward and backward pass. So basically, you will first give your first image, and the memory utilization will increase with as you do the forward propagation. And in the backward propagation, it will decrease. So as you can, and then you will repeat the process for the other images. So as you can see that here we have both free memory and the compute available. However, the model parallelism is not using that free compute and free memory. So that's why we are not seeing very good performance with the model parallelism. So is there a way to improve this? Is there a way to improve the performance, or is there a way we can solve this issue? So that's why we need memory aware designs. So that's why we propose GEMS, which is a GPU enabled memory aware model parallelism system that offers 2 strategies, master and master, that can solve the above problem. And we have also integrated our memory aware designs with the data parallelism so that we can scale it to higher number of GPUs. So let me give you a high level idea of our memory aware design. So you will do the same thing with the first image, like you will apply the forward pass, and during the backward pass, as soon as the last GPU is done with the backward pass, you can train the another model replica. So basically, like since you have a layer 1 on the GPU 1, and let's say layer 100 on your GPU 4, then as soon as the last GPU 4 has completed the backward pass, then you can start the forward pass for the layer 1 on GPU 4. So you are training the model in an inverted way. And since you have 2 replicas, so that's why you will need the Allreduce also. Let me change my pointer. I have to minimize my screen. Okay. So yeah, so that's why we will need the Allreduce in the end, so that we can synchronize the gradients. But even with this communication overhead, we are seeing the large improvement since we are able to use that free compute and the free memory available. So let me show you the results. So we have tested the GEMS on up to 1024V100 GPUs. So here I am showing the results for our 2 memory aware designs integrated with the data parallelism, and we are training the ResNet 1K model on 512 into 512 image sizes. Since it is a very large model, so that's why we need at least 8 GPUs to train this model. And even on the 8 GPUs, the maximum batch size is 1. So on 1024, we have 128 replications. So as you can see that even on the 8 GPUs, we are able to get a very good performance than the basic model parallelism. And on 1024, because of the optimized point-to-point and collective communication in MFH2 GDR, we are able to scale it to the, we are able to achieve near linear speed up and we get 97.32 scaling efficiency. And on 1024 GPUs, we are like 4x better than the model parallelism basic model parallelism. So now let's move to the application. Like, how can we exploit these designs to train a actual model in digital pathology? So in pathology, we have very large images, like 100,000 into 100,000 pixels. And so definitely these images cannot fit inside the memory of single GPU. So that's why we do tiling. But even with the tiling, the maximum batch size trainable on single GPU with our model parallelism is like 224 or 300. So if you're using that tile, then you will, if you're using that smaller tile, then you will lose the structural information. So that's why using GEM, we enabled the training on larger tiles like 1K into 1K or 2K into 2K. And we were able to reduce the training time from 32 hours to just 27 minutes using our optimized algorithms in GEMS. So with this, I conclude my talk. So we talked about the need for the model parallelism, and we also talked about why the model parallelism is not giving good performance. And so that's why we proposed and designed the GEMS framework and achieved 97.32 scaling efficiency on 1000 V100 GPUs using MUG'20 GDR. Okay, thank you. If you have any question, I will be happy to take it.
Yeah, so I don't see any questions yet on the QA box. So might be we can continue with Aamir's first presentation on the Dask.
Yeah.
Right, so my slides are visible?
Yes, yes.
Right, so my name is Aamir Shafi, and this is some work that I've done with my colleague Jahanzeb, Hashmi. The title of this talk is Efficient Communication Support for Dask using MUG'20 GDR. So we have recently started looking at data science ecosystems, and Dask is apparently one of the popular ones, which is heavily adopted by the Python community. So we have been looking at opportunities to support efficient communications and this is some work in that direction. So Dask is a popular task-based distributed computing framework. This is recently being adopted by NVIDIA as part of their Rapids framework. And I will also talk about Rapids framework in my next talk. So within the Dask environment, there is a library called the Dask Distributed Library. And this library is essentially responsible for supporting parallel and distributed execution of Dask programs. So I will just briefly, go into a little more detail of this. So in this picture, you can see essentially a scheduler process, and the scheduler process has a number of workers that are connected to the scheduler, and essentially these scheduler, along with these n number of workers, they form what is called a Dask cluster. These workers can dynamically come and join or leave the cluster. And once the user is ready to execute his or her application code, they may do so using this client process. So, and this client process obviously is also going to join dynamically. It will connect to the scheduler and give the input data, which is then processed by the worker processors. So in this context, there are some particular communication requirements of Dask, which include scalability. Obviously, we would like efficient communication. Elasticity is a unique requirement because these workers and clients, they come and go. And then there's also something called support for coroutines. So this Dask distributed library is implemented as an asynchronous IO application. So this is a Python specific term. There are some applications in Python that implement a framework called async IO. So if we have to implement communication functions or operations, we may not do so using regular Python functions. We have to write what are called coroutines. And then obviously the last point is, like, we also require efficient communication to from GPU memory. So in this work, what we have actually tried to do is that there are two existing communication devices for Dask. One is a TCP-based device, and the second one is UCX-based, which uses a Python wrapper called UCXPy. And this UCXPy layer is essentially the layer of software that provides these communication coroutines, which are later used by the Dask runtime. And in this work, what we have essentially done is that we have developed an alternate communication device that we call MPF for Dask, which essentially uses MUG'2 GDR. Obviously, this is all done from the Python code. So for that reason, we have to rely on a Python wrapper library. In our case, we use something called MPF for Py. So MPF for Py is an external project. It has been there for some time. So just the Dask architecture, the top two layers are essentially different components of the Dask ecosystem. I will not focus on them right now. Our focus is on this layer called the distributed, which is providing the support for distributed computation, and it is also providing support for communication. So as I said, there is a TCP device, and then there is a UCX device that relies on UCXPy. And what we have done as part of this work is that we have essentially introduced this MPF for Dask that uses MPF for Python wrappers to essentially exploit, communications provided by MUG'2 GDR. So here are some latency and throughput comparison results. So on the left-hand side are latency numbers, and on the right-hand side are throughput numbers. So these are internode numbers, and I just want to focus on two lines here. This black line is essentially a UCXPy, and this maroon line or the red line is essentially what is MPF for Dask. And as you can see in this picture, that irrespective of the performance differences between MUG'2 GDR and UCX, at the Python layer within the communication routines that we have implemented, we are able to gain like 6 times speed ups for, let's say, 1 byte messages, and overall up to 256K, we are able to achieve better performance than UCXPy. And here we are running the UCXPy can execute in 2 modes. One is called polling mode, one is called event mode. So we are actually using it in the efficient mode, which is the polling mode. And we see the similar trend here in throughput. Here for large messages, 2 MBs and beyond, we are able to see this maroon curve is able to gain 4 times more throughput than this black line, which is UCXPy. So we then utilize MPF for Dask in a couple of benchmarking applications. So this first benchmarking application, this is provided by the Rapids project as part of a library called Dask CUDA. In this, you can see that this the yellow line is UCX. Essentially, by UCX, I mean the Dask using UCXPy layer, and this red line is bar is essentially MPF for Dask. And as you can see, we for the execution time and for the communication time, we are doing significantly better than the UCXPy. And this is essentially the performance difference is coming from our implementation of the wrappers for MPF for Dask. So we observe similar trends for the second benchmarking applications, and in this case, we basically do better for execution time, 3.11 times, and for the communication time, it's been reduced by 3.22 times as compared to UCXPy. And this picture is basically presenting throughput comparisons, and again, we see significant performance increases like 6.57 times in 6 worker case for MPF for Dask, and in the case of this other second application, the throughput is increased by 3.74 times. Comparing MPF for Dask with UCX. So with this, I conclude my talk. So we have, as part of this work, we have developed MPF for Dask, which is a new communication backend for Dask. It basically uses MPF for Py over MUG'2 GDR, and essentially the performance gain is coming from efficient implementation of communication coroutines in the MPF or Dask layer. So thanks a lot for your time. And if there are any questions, I'm happy to take those questions.
Yeah, Aamir, thanks. I don't see any questions yet on the Q&A box. So might be we'll switch to Qinghua. If you can share your slides and start presenting.
Yeah, Dr. can you see my screen?
Yes, yes. Put it in the presentation mode.
Yeah, sure. Is it okay?
Yeah, yeah.
Okay. Okay, thank you, Dr. for the introduction. Hello, everyone. I'm Qinghua Zhou. So today I'm going to share my recent work, the benefits of GPU-assisted on-the-fly message compression with MRPG to GDR. So this work mainly focuses on the GPU-to-GPU communication of megabytes message. So for the state-of-the-art communication library like Spectrum API and MRPG to GDR, in the past they have optimized a lot, but the bandwidth of GPU communication saturates the IP network. So for this messaging range, for some HPC application like the AWP-ODC, which is a well-known simulation application. So with larger problem size and more GPUs, so the communication time will become significant. So we may think new techniques to further improve the GPU communication performance at this messaging range. So the compression is a classic method to reduce the data size. So for the scientific data, they can reduce the size and lower the pressure on network with limited bandwidth. And in the past, some CPU-based compression algorithm has been integrated into MPI libraries, but those CPU-based compression algorithm is still time-consuming for GPU communication. And with the advanced GPU computing power, so many GPU compression algorithm has been developed. So in this work, we want to integrate the GPU-based compression algorithm into the MRPG to GDR to achieve high performance on-the-fly message compression. So here we list some existing compression algorithm for the floating point data. So basically there are two kinds of compression algorithm, lossless and lossy. So for lossless compression algorithm, they guarantee that there's no compression error after compression and decompression. And so you can see for the lossless compression algorithm, different algorithms support a GPU or CPU or another support like a single or position. But the one disadvantage of the lossless compression algorithm is that they generally they will achieve low compression ratio. So in recent studies, scientists developed some error-bounded lossy compression algorithm to achieve higher compression ratio. So here we pick two compression algorithms, MPC, which is lossless, and ZFP, which is lossy, to study. So here we test these two compression algorithms on NVIDIA Volta 100 GPU. So here we test the performance on different data set, and we found that both MPC and ZFP, they can achieve very high throughput, match with the PCIe bus or IP network. And for MPC, the compression ratio is generally low compared to the ZFP. So for ZFP, currently the GPU version support the fixed compressed rate. So that means, so for each floating point data, they will compress to fix the number of bits. So here for the 16 bits, for the 32 bits floating point data, we will get compression ratio 2. So we integrate these two compression algorithms into MUG'20 and evaluate the performance on two kinds of clusters. So Frontier Longhorn, each node has 4 300 NVIDIA GPUs. Frontier Liquid has 4 RTX 5000 GPUs. And for the intranode GPU to GPU interconnection, Longhorn use NVLink 2 and Frontier Liquid use PCI Gen 3. For the internode interconnection, Longhorn use InfiniBand EDR and Frontier Liquid use InfiniBand FDR. So this is the internal device-to-device latency. We run OS benchmark on these two clusters. So we compared our proposed design with these two compression compared to the baseline. So the baseline is the default MRP2 GDR without compression. So as you can see, within the message size, we got more benefits. So for MPC, on Longhorn, it achieved, it reduced the latency up to 62.5% at 62 megabytes, and on Frontier RTX, it reduced the latency up to 77.1%. For ZFP, we tested different compressor rates. So the lower the rate, the higher the compression ratio. So it reduced the latency up to 78.3% on Longhorn, and reduced the latency up to 83.1% on RTX. So this is the result of internal device-to-device latency. So first we look at this figure. So the internal latency, the trend is similar as the internode, because on Frontier RTX, the internode interconnection used PCI Gen 3, the throughput is lower than the MPC, than both MPC and DFP compression decompression throughput. So the trend is similar. So MPC reduced the latency up to 60.6%, and DFP achieved reduced latency up to 79.8%. But on Longhorn V100 nodes, we didn't see benefit of the of MPC. That's because on Longhorn it used NVLink for the internal GPU to GPU. So NVLink is faster than the throughput of MPC compression decompression. But for DFP, start from 8 megabytes with the rate 8 or 4, it can still get benefits. So it reduces latency up to 40.5% at 32 megabytes. Now we evaluate our design on the real-world application, AWP-ODC. We tested the weak scaling on Longhorn V100. So we got a good benefit. So for MPC, it achieved up to 21% improvement on 64 GPUs with 2 GPUs per node. For ZFP, with the rate 8, we got up to 37% improvement on 16 GPUs with 1 GPU per node. So now let me conclude. So we integrate 2 kinds of compression algorithm into MRP2 GDR. So we implement the compression for point-to-point GPU to GPU communication. On benchmark level, both the internal latency and internal latency show benefits with MPC and ZFP. And on application level, the AWP-ODC achieved up to 21% with PC and 37 with ZFP. And the compression feature will be available in the upcoming GDR release. So that's all. Yeah, I'm happy if you have any questions.
Yeah, so Qinghua, I don't see anything yet on the Q&A box. So there is some, for the previous talk, Dask talk, I think there's something discussion going on the Slack. So let's go to the final short presentation. Aamir, you want to continue?
Yes, Dr. Parna, can you see my slides?
Yeah, in the QML paper, yes. It is in the next slide is showing up.
Yeah, so, okay, so.
I think something is getting cut down from the right-hand side in your slide.
Yeah, that's, let me share again.
No, I think it's still being cut. I think you can just open the PowerPoint and share. I think that might be easier.
This is PowerPoint, Dr. Parna. So,
if you are using two screens, can I suggest just using one screen? Yeah, this is fine.
Yeah.
Okay. Okay, so Aamir Shafi here again. This is work done with Madhiye Ghazimir Saeed and Quentin Anthony. So in this talk, I'll be talking about introducing support for machine learning applications using MUG'20 GDR. So here is an overview of the Rapids project. So this is NVIDIA's project, and what they're aiming to do is to accelerate end-to-end data science using this project. So the idea in this particular case is that once the data preparation stage is being done, so the data comes into the GPU memory, and it essentially stays there. You know, we do the training on in the data which is stored in the GPU memory, and also do visualization for that. And obviously, in order to do that, so this project is aiming to develop support for different components of data science. And for this particular talk, we are interested in exploring the support for machine learning algorithms, and for that, the most relevant library is QML. So we will be introducing MUG'20 GDR support for communication, specifically training in the QML library in this particular talk. So a little bit of an introduction of QML. So QML is essentially a collection of machine learning algorithms and some mathematical primitives for GPUs. In the Python community, scikit-learn is considered a standard for machine learning tasks, but scikit-learn is CPUs only or host-based only library. So essentially, QML is trying to become the GPU counterpart of scikit-learn. What the Rapids framework does is that it has essentially adopted the Dask ecosystem for scaling out, right? So for specifically this multi-node, multi-GPU setting where they would like to exploit a cluster of GPUs, what QML essentially is committed to use is the Dask ecosystem. And typically we have seen in the Python ecosystem, so I'm trying to point to this picture on the right-hand side. So Python essentially is popular because it's really easy to use. There is support for a lot of libraries in the Python programming language. But obviously then since it's an interpreted language, there is a performance compromise. And the way most of the production Python packages are handling this constraint is that they essentially utilize underlying C++ libraries, and then essentially develop these wrappers for essentially exploiting high-speed implementations in the native languages. And QML essentially has a similar architecture. So if we just look at the left-hand side here, so on the top we have the Python API, which is exported to the users, and below Python is a Cython. So Cython is a wrapper that allows calling C++ code from Python layer. And most of the ML algorithms and these primitives, they are essentially implemented, in the QML stack in the native programming language like CUDA and C++. However, the API is still Python, so it still makes use of the Python ecosystem. Here is a QML execution model with Dask. I've shown this picture before, but now I've added some more components here. In the multi-node, multi-GPU setting, the way QML executes is as follows. So first, they essentially rely on the Dask ecosystem to scale out. So which basically means that the Dask is going to start n number of workers. So in this case, we have 3 workers here, and all of these are connected to the scheduler. The client is going to come connect to the scheduler and submit the code for execution. But the communication between these workers is point to point, and currently it's supported by UCX. So in the other work that I presented, we showed that we are able to utilize MPX communication for that as well. But in QML, they're kind of using an overlay communication layer, which is shown here as these red arrows. And for the default implementation of QML, this is essentially the Nickel communication library. So let me just say that again. So first, we basically start execution using the Dask cluster. So all these gray boxes come up like client, scheduler, and these 3 workers. And once the workers boot, they are essentially QML processes. Within each worker process, they then initialize the Nickel communication library, which is kind of an overlay communication library, and they utilize these efficient communication library for communicating between QML processes. And the reason they are doing this is obvious, because Nickel has optimized communication collective functions that they would like to utilize. So in this work, what we are doing is that we are, instead of using Nickel, we have introduced support for MUG'2 GDR for QML algorithms, and we essentially do that. In this picture, you can see these yellow boxes. So again, Python layer, Cython layer. This is the native C++ CUDA code that implements ML algorithms, all these primitives. So there is this support for Nickel, but instead of using Nickel, what we are doing is that we are introducing support for MUG'2 GDR using MPF or Pi. And here are some results for different algorithms. So for example, in this picture, we are showing k-means and random forests. And as you can see, here we are showing results, scaling results from 1 GPU to 32 GPUs. And we are actually able to get 1.6 times speed up on 32 GPUs. MUG'2 GDR is performing better than Nickel for 32 GPUs. We get some performance benefits for random forest, but random forest is one algorithm. The current implementation in QML, it's not utilizing any collective functions. So for that reason, the performance gains are modest here. For other algorithms like nearest neighbors and truncated SVD, we see similar patterns, 1.24 times the speed up. And again, for truncated SVD, 1.24 times the speed up. We also see a similar pattern for linear regression. So we are observing 1.25 times the speed up on 32 GPUs. And this graph on the right-hand side is essentially plotting, GPU implementation versus a CPU implementation. So in this case, obviously, the GPU implementation is, performing better than an optimized CPU code as well. So these graphs are for these bar graphs are for different QML algorithms that they are supporting right now. So with this, we conclude. So again, QML is a suite of ML algorithms and primitives from the NVIDIA Rapids framework. It basically scales out using a Dask. And when it's executing in multi-node, multi-GPU setting, which is typical cluster of GPU scenario, QML by default uses UCX and Nickel. And in this effort, what we have done is that we have replaced, or we have introduced support for MUG'20 GDR inside the QML library. And typically the algorithms that I've shown rely on these three collective primitives, mainly Allreduce, reduce, and broadcast. And what we have been able to observe is that, you know, we have ported these 5 ML algorithms so far, and on average, we have seen that MUG'20 GDR is performing on average like 1.3 times better than Nickel. So with this, I conclude. Thank you for your attention. If there are any questions, you can share here in the QA box, or I'm happy to answer them on the Slack channel.
Yeah, so thanks, Aamir. I have not seen any questions yet on the QA box. So then we'll move to, we are running a little bit late. The next session is actually the open mic session. So typically we do that